Hello, good morning, everyone. Let's start with a little bit of recap of what we've learned last class. So this is the study guide, and I think it's second page. Right, so I'm just going to label some of these things to help you remember them while we wait for people to, trickle in throughout the morning. So page 2 of the study guide. Label the chambers of the heart. So over here, on the left side of the diagram, which is the right side of the heart, that would be the right atrium. Okay, to save space, I'm just going to put R, but it's the right side. And below the right atrium, we have the right ventricle. Okay. On the other side, we have the left atrium. And the left ventricle. Now, generally speaking, we have the oxygen poor side, oxygen poor blood on the right side of the heart, right? Just returning from the body. Okay, so that's O2 poor, and we have the O2 rich blood over here. Okay, O2 poor, O2 rich. And of course, we want to separate it. So does anybody remember what's the name of this structure that I'm shading in right now?
Septum.
That is the septum. Very good. So SCP-TU. All right, let's take a look at the other side. Label the structures leading to and away from the heart. Basically, we're naming the vessels. Right? So we have the superior vena cava here. And then, of course, we have the inferior vena cava. Right? Those are oxygen poor. Like that. This one over here is also oxygen poor, even though it is an artery. And we are taking the blood from the heart to the lungs through this vessel. So that would be the pulmonary artery. This one's on the left. And we have the other side as well. Over here, that would be the right pulmonary artery. Okay. Returning from the heart, we have these veins. Okay, they are red now because the blood has just been to the lungs where they picked up oxygen, and we will call them pulmonary vein. Okay. Veins, you have more than one. And over here, it will be right pulmonary vein. Okay, and of course, they will then go into the left atrium. But those are the main vessels. I am missing one here, I just noticed. Okay, can someone tell me what that is?
The aorta.
That is the aorta. Very good. The aorta continues to come down, right? Remember? Like that? Okay. And it branches into little smaller ones. Goes to the right side and the left side of the body, as well as to the head, the carotid artery, you might remember from last time. Okay. Moving on. Label the 4 valves of the heart. We have this one here on the right side and this one here on the left side. This is the tricuspid. Tricuspid valve. And on the other side, we have the bicuspid. Right? And they belong to the same group. They open and closes together. And the name that we use for both of them is the AV valve, which is atrial ventricular valve, right? AV valve. Now the other ones, which is right here and there. This one is inside the pulmonary artery. So that's the pulmonary valve. And over here we have the aortic valve. And what do we call them? The purple ones. What is the collective name for these purple ones?
Semilunar valves.
The semilunar valves, that's right. Thank you. Okay, that's it. Okay. Remember, when the yellows are open, the purple ones are closed. But when it's time for the purple ones to open, the yellow ones will be closed. Okay, they like kind of operate in out of phase manner. All right, next part here is asking us to trace the blood flow. And so we know it's going to be coming in from the superior and inferior vena cava. And then from the vena cava, it's going to go into the right atrium down to the right ventricle. It's going to go through these pulmonary arteries. Then it's going to go to the lungs. Then they will come back. They will come back. Right? Through the pulmonary veins into the left atrium, left ventricle, and then it's going to go through the aorta to the left side of the body, to the head, to the right side of the body, and it will also come down through the abdominal aorta as well. That pretty much summarizes like 90% of what we learned last class. Does anybody want to ask anything, any follow-up questions before we, move on to today's stuff? Okay. I think there's another question here that I want to do, number 10. A patient has a breathing rate of 30 breaths per minute and a heart rate of 70 beats per minute. If their stroke volume is 80 milliliters per beat, calculate the cardiac output. So this was like the last thing we did last time. I don't know if you wrote it down, but let's go through this again. So cardiac output, okay, which is the volume of blood. I mean, it could be milliliters, could be liter. We'll convert it in the end, okay? That is being circulated per minute. And that's useful as an indicator for various things, okay? Like to assess how healthy your heart is, for example. And that equals to the heart rate, which is beats per minute, multiplied by the stroke volume. Stroke volume is volume of blood that comes out of the heart when it's squeezed. Okay, every time it beats, how much blood comes down. So in this question, we have 70 beats per minute multiplied by a stroke volume of 80 milliliters per beat. So we can cross the beat out. 70 times 80 is 5600. Okay. Or we can say 5.6 liters per minute. Okay. You can just divide it by 1,000 because there are 1,000 milliliters in a liters. Okay. So just familiarize yourself with this. There will be at least one calculation questions, right, on the quiz that uses this formula.
A quick question.
Mm-hmm.
So the breaths per minute, that's just like trying to confuse you background information, or?
Yeah, totally trying to confuse you. Yep.
Okay. We're not there yet. Okay.
Yeah, we don't need it yet. Okay, that's all. Okay, hope you're all warmed up now because today we have a lot of things to learn and a lot of notes to take as well. So let's get to it. There we go. All right, next topic in this lecture is the cardiac cycle. Anybody know what this picture is showing? Like what? This is a chest X-ray, okay? Like you see the ribs here, but like what is that? Why
Is that a pacemaker?
That is a pacemaker. Very good. Okay. What does a pacemaker do? Anyone, or go on medicine if you want. Yeah.
I'm pretty sure it paces your heart so it doesn't beat too fast, and there's something to do with little electric shocks.
Yeah, that pretty much summarizes it quite well. Okay. So your heart actually create its own electrical signal on its own rhythmically, and that sets how fast your heart beats. When that fails, okay, or when it's not doing it properly, then you might have arrhythmia, like uncontrolled heart rates. Like your heart might be fluttering. Some people say, like not in a good way, right? So then you would need to have a pacemaker, right? The electronic device here that would set the pace for you. Okay, that would override your own electrical signal, and it basically, keeps your heart rate in check. So more on that later. But that's what it is. Okay. So the cardiac cycle is basically everything that happens during one heartbeat. Okay, so I told you already the atria on the top will contract simultaneously at the same time, and then that causes the blood to come down to the ventricles. And when the ventricles are filled up, then it's time for the ventricles to contract. So when the atria is squeezing, ventricles are relaxed. But when it's time for the ventricles to squeeze, then the atria is going to be relaxing. So contraction of the heart muscle is called systole. Systole. So whenever a chamber is undergoing systole, whenever it's contracting, it is emptying. Okay, so it's like getting the blood out of it. The opposite of contraction is relaxation. That's when the heart muscle is, just not squeezing. It's just relaxed. We call that diastole. So that's how you pronounce it. Systole and diastole. So when it's relaxing, then it's filling. Okay, filling with blood. So keeping this in mind, let's talk about this one more time. When the atria is undergoing contraction, it's emptying the blood. And the blood is going down to the ventricles, right? So the ventricles must be in a relaxed state so that it is filling up. Okay. Stay with me. Once the ventricles are filled up, then it's time for the ventricle to squeeze. When the ventricles squeeze, The right side will go to the lung through the pulmonary artery. The left side will go to the aorta, right? So it's emptying. But when the ventricles are squeezing, as they're emptying, now is for the atria to relax. And when they're relaxing, they're filling up. So think about it, right? What's causing the atria to fill up? What's feeding blood into the atria? Well, on the right side, it would be the superior and inferior vena cava. On the other side, it would be the pulmonary vein. Right? So it's always filling and emptying, filling and emptying. Okay, I'll write all this stuff for you down. I'll write down all this stuff for you later on. Okay, but systole, contraction, diastole, relaxation. So we have a natural pacemaker in the heart. Okay? A natural pacemaker is a group of cells, a cluster. Cluster means a group, right? A group of specialized cells that are in the heart, and under the control of your nervous system, right, of your brain, it will rhythmically send out electrical signal. Okay, so these electrical signal, we call them an impulse. Okay? Long story short, these electrical signals will cause the heart muscle to contract. Okay, but the whole heart is not going to contract all at once. Right? I told you already, atria goes and then ventricle goes, right? So the contraction will not occur until the signal gets to that part of the heart. Okay, so the signal originates from the natural pacemaker, which has a name. It's called the SA node. SA node, sino-atrial node. You can just say SA node, but that's what it stands for. And this is located at the right atrium, right? Just where the vena cava is coming in, where the superior vena cava is coming in, right? So I want to show you this on a picture. Right? So there is the SA node. Okay? On its own, it's able to send out these impulse, right? And the impulse, the electrical signal, will spread throughout the heart and cause the heart to contract. Okay. Remember, the SA node, I'm just going to go back here in the previous slide. The SA node is under the control here, controlled by the nervous system, which we'll learn later. Okay. One division of your nervous system is called the autonomic nervous system. It does everything in the background for the body. These are things that we don't think about. It just happens in the body, like the heart rate, okay, like the movement of your digestive tract. We don't have to think about that. It just happens on its own, right? So the nervous system is gonna take care of the heart rate for you, which is a good thing, right? Like we don't want to have to worry about, you know, our own heart rate. It's not like, oh, okay, I gotta remember to for my heart to beat, okay? Otherwise, like I'm gonna die, right? So it's a good thing. It's an automated process. Even though we cannot control the SA node, right? Even though we cannot control how fast our heart beats, not like by our minds, anyways, okay? But there are things we can do to influence the SA node. For example, right now, if you want your heart rate to go up, what is something you can do right now? And then your heart rate is going to go up almost immediately.
Run.
Someone can scare you, yeah, or you can run.
You can run, right? As Patrice says, and medicine says you can, someone can pop into the room right now and give you a jump scare, right? So we can say it's influenced by physical activities, right? right? Like if you're running, heart rate's going to go up. If you're doing yoga, heart rate's going to go down. By stress, right? Well, actually, not necessarily stress. Like you were saying, someone gives you a jump scare, but it's not the jump scare that causes your heart rate to go up, right? When someone scares you, your body releases. Anybody know what I'm talking about? What does it release? Let's think of it like on a roller coaster. What's released by the body that
Like
makes?
the fight or flight instinct.
That's right. So anybody know what the hormone is? If I say it, you guys will know it. I'm sure you've heard of it before.
Dopamine?
Good try. Anyone else? Yes. Korea said adrenaline. Okay. So when you have the adrenaline, right, or the epinephrine, some people call it, that is going to cause your heart rate to go up. Right. So it's influenced by physical activities, hormones. You can rise such as adrenaline. And what else? What else can cause your heart rate to change? Are any of you guys drinking anything this morning?
Caffeine.
That's right. So if you're drinking coffee or like I'm drinking tea right now, there's a bit of caffeine in it, and caffeine can cause your heart rate to change, right? So like chemicals. Do you understand? Right? So even though we don't have a conscious control over our heart rate, we cannot tell it to speed up or slow down just by thinking about it. There are things that we can do to the body that would affect, how fast it's beating. All right. So that's the SA node. That's the natural pacemaker, which is right here. Okay? Now I'll put this in nice notes for you afterwards, but just try to understand what I'm saying here first. Okay. So the SA node, it's located on the right atrium. It's a cluster of cells, and it's gonna send these electrical signals. Okay. So the electrical signal is going to spread across the atria. Okay. It's really fast. It just goes across. Okay. And then it will cause both of the atria to squeeze. Now, when they are squeezing, the electrical signal has not passed down to the ventricles yet, right? That's why only the atria will squeeze, but the ventricles are still relaxed at this point, which again is what we want, because when the atria squeezes, the blood is filling up the ventricles. You want the ventricles to be relaxed. Okay, so the blood goes and fill up the ventricles. Now the signal is going to spread down a little bit, and as the signal goes further away from the SA node, it weakens. Okay, like if you have Wi-Fi at home, there are some spot in your house or in your apartment that doesn't really quite get the signal, right? Because it's like too far away from the router or something, right? So that's the same thing here. The signal gets weaker and weaker, and that is why there is a second cluster of cells right here. Okay? That is called the AV node. The AV node is going to boost the signal. Okay, when it receives the signal from the SA node, it boosts it. So it strengthens it again, such that it can travel further in the heart. It's like a Wi-Fi extender. All right. So the AV node will take the signal, and then it will pass it down a bundle of special conducting fiber called the AV bundle. Right? And the AV bundle is in the septum. Okay, it goes down, and then finally it comes up on the side. Right? And these are called the Purkinje fibers. Right? So now when the signal gets down here, it will cause the ventricles to squeeze. Now I want you to pay attention to the direction of the arrows here. Right? The signal goes down the septum. Septum is not going to contract. Okay, septum is just conducting the signal, passing it on. But when the electrical signal goes up here on the side through the Purkinje fibers, it will cause the ventricle to squeeze from the bottom and up. Right? Physiologically, it makes sense because the artery is on top, and then the aorta is on top, and the pulmonary artery is on top. So this upward squeeze motion really causes the blood to shoot up. Okay. Now, if I have lost you in all that, basically this is the conduction system. Okay, you start with the SA node. That's just automatic, right? It's just, if your heart rate goes faster, then it sends out the signal faster. And then if you relax, the signal goes slower, right? These are electrical signals spread across the atria, and then it goes to the AV node for a boost. The AV node sends it to the AV bundle, and then it sends it to the Purkinje fibers. Okay, so that's the path that it takes. Now I want to write this down for you in terms of what's exactly going on when the signal is passing through these structures. All right. If you have the study guide, you can take it out. If you don't have it, just copy it in a separate piece of paper. So there's a diagram right here. And this is like towards the end. All right. So here we go. We have the SA node here, right? And then we have the AV node here. So let's write down what happens first. Okay. Give you a moment to find this page if you haven't already. Okay. SA node. So it's gonna send the signal across the atria, right? Impulse means the signal spreads across atria, like across. And at the same time, some of it is gonna go down to the AV node. Okay. So these two things happen simultaneously. But what I really want you to understand and visualize is all the things that are happening when the signal gets across the atria. So atria undergo systole. You know what? Let's just keep it simple. Atria contract, okay, which is called systole, right? And when it's contracting, are we emptying or are we filling up? You don't have to tell me. You just think about it, okay? Systole, squeezing. When you squeeze something, it's emptying, right? Squeeze a juice box and you will see the juices are coming out. So if you squeeze the atria, the blood is coming out. So atria, empty the blood. Well, when you are emptying the blood, they have to go somewhere. They would go to the ventricles. But to do that, we have to open AV valves. Huh? I'm going to open the tricuspid valve, open the bicuspid valve, and then the blood's going to come down. Okay, the contraction of the atria is very gentle. Okay, it's not like that. Okay, like because gravity is doing most of the work, right? It's just like gentle nudge, and then the floor opens, right? The floor being the tricuspid and the bicuspid valve, and then the blood will automatically drop down. Okay, and for the ventricles to fill up, they need to be relaxing. So ventricles relax diastole. And then ventricles fill up with blood from the atria, right? Like obviously. And last time we were saying, when the blood is coming down and filling up the ventricles, we don't want them to escape. We got to close the exit, right? I keep on saying, right? We don't want the blood to prematurely go into the atria, to the aorta. We don't want the blood to prematurely go into the pulmonary artery. So we gotta shut the exit, right? So we close semilunar. Okay. So all this is happening when the signal is spreading across the atria. Are you guys with me? Anybody have any questions? I hope this is clear. All right, fantastic. So at the same time, when all this is happening, when all these things are happening, the signal is also spreading down to the AV node, right? So AV node is gonna boost the signal, is gonna pass it to the AV bundle. Okay, sometimes if you read online, there's like more stuff in between, but whatever, we're just gonna call it AV bundle. And then it's gonna go to the Purkinje fiber. Okay. I'll come back to this in a second. I just want to label these things for you. So all these things here, right? We just call it AV bundle. And this one, it's like supposed to be right pointing at these things. Okay, so these little fibers here, those are the Purkinje. Purkinje fiber. Okay. So once it gets to the Purkinje fiber, it's time for the ventricles to contract, right? The chambers are only going to contract when the signal gets there, right? So it's basically opposite of all these things, right? So now the ventricles contract, right? And send blood to pulmonary artery on the right side and aorta on the left side. Okay. But for the blood to go through them, you have to open semilunar valve. Okay. You probably have to reorganize the notes afterwards anyways, okay? Like I know it's very messy. I'm sorry. I'm just kind of doing it on the spot. Okay. PA is pulmonary artery, huh? So you open the semilunar valves. And now all the blood is going forwards. You want to make sure that they're not going back. That's why we have to close the AV valves. Right? Tricuspid and bicuspid have to close. What are the atria doing right now? What's going to be happening to the left and right atrium? Are they squeezing? Are they relaxing? What's going on with the atrium?
Relaxing.
They are relaxing. That's right. Okay, so atria, relax. It's done. They already finished contracting, right? So relax and get filled up, right? By blood. Right? So from superior and inferior vena cava on the right side, and pulmonary vein on the left side. Okay. So closing the AV valves achieve two purposes. Okay. The atria are filling up with blood. We don't want the blood to drop down to the ventricles just yet, right? It's not filled up yet. So we have to close the AV valve, right? That's the first purpose. Purpose number two is the ventricles are squeezing. We don't want the blood to come back up either. Right? So by closing the AV valve, we can prevent the blood from going down prematurely, and we can also prevent blood from shooting back up from the ventricles. Okay. And then once the electrical signal dies off, then it's time for the ventricle to relax again, and then it repeats. Of course, all these things happens, you know, in a heartbeat, right? Just like, and then it's done. So it's like super fast. Okay, that's all. Questions, comments, follow-ups? Okay, moving on. So when the conduction system fails, then it could lead to arrhythmia. Right? Arrhythmia is basically inconsistent heart rate. Like the heart rate could be going really fast all of a sudden, but it could also be really slow. It depends on what the problem is. Okay, and there are different severity with arrhythmia. Some you can just monitor and see what's going to happen, and you know it won't really affect the person. Sometimes they need to take there's some medication that you can take like at the hospital. It literally stops your heart for a little bit and reset it. Okay, you guys remember ATP, right? What does the A stand for in ATP? Anybody remember that?
Adenosine.
That's right. So adenosine is actually a medication that can reset the heart. You can search it up on YouTube. I think there's some video. You can literally see the person gets an injection of the adenosine, and then the doctor will be like talking to them, and then you can see them like just pass out for 1 second and then comes back. Okay, so that's like the heart just stop momentarily, and then you know it comes back and beating normally again. Okay, it's quite scary and you know amusing at the same time. So in some cases where you know those methods don't really work, then you have to implant the pacemaker. Okay, so there's the thing is not in the body. Okay, for goodness sake, this thing is like basically on the chest, but then the wires actually you know would be going into the body, and you know you have to change the battery and stuff like that every now and then. How is it charged? Yeah, like it's battery. Okay, like it's not like there's a USB and you plug it in or something. Okay? Like there is battery that you have to change periodically. Remember the device is outside, right? Sorry, what's that?
I was like, oh, you go in there and like get your AA batteries and
I don't think it's AA, but it's those the cells, right? I think. Yeah. Okay, so we can look at the electrical signal through a non-invasive technique, right, called the ECG. Right? Usually, I would have students in class who have done an ECG before at the clinic or something. I had an ECG done, a couple of times, and they just stick these little stickers, basically, right? But they are probes that detects electrical signals that is spreading out throughout the body, and it would come out to a graph that looks something like that. Okay, so this is a typical normal ECG, right? That shows the signal that are generated by your heart. Okay, and this is a very quick way for a trained health professional to see if something's wrong with your heart rate. Okay. I will come back to this in a second. You don't really have to be a trained professional to see something is wrong with this, right? You guys seen this, right? Like this thing on TV, or when you watch, I don't know, like any shows, like if anybody is at the hospital, they would be hooked up to this thing that go beep, beep, right? That's the ECG essentially. Okay. So that's what the normal one looks like. And if you see something like this picture, right? Like something's wrong, right? What do you think is wrong here? Just like wild guess.
Not beating fast enough, so it's low. That's what bradycardia means.
That's right. It's really slow, right? Look, the peaks are really, really far apart, right? So this is bradycardia. You don't have to know this word, okay? I'm just showing you. Yeah, brady means really slow. Okay, bradycardia. And this one is tachycardia. Tachy is really fast. Okay, this one is harder to tell. Without a normal one for reference, it's hard to tell. Okay, and then this is ventricular fibrillation. This is really bad. Like if we don't help this person, the person is gonna die, within a couple minutes. Okay, this is when the ventricles are, not producing meaningful squeezes. It's just like undergoing spasm, and it doesn't really know what's going on. So in this case, that's when you need to have the defibrillator, right? The defibrillator, like again on TV, you probably have seen it. They go like clear, and then they shock the person, right? So that electrical shock is hopefully, in the best case scenario, going to reset the SA node. Okay. So when you apply an external current to the SA node, sometimes it's able to reset it. Okay. So nowadays you would have these AED, right? In the malls, if you're on campus, you can look around. They are everywhere. Okay. So these things, you don't even have to be a trained professional. Okay. Like you open it, you stick the sticker on, and you press the button, and then it automatically charges up and then deliver the shock, right? Okay. So it's just like more accessible, right? Than before. And it could save a life sometimes. So what are the different parts of the curve? What do they represent? Well, I'm not going to go through the whole thing, but there are a few things that are important. Okay, so like the first little bump here, first little spike in the graph, that corresponds to the signal generated by the SA node and spreading across the atria. Okay, so you see this, we'll say atrial contraction. Okay, it's not a big spike, and I told you several times already, the atria just gentle squeeze, right? Gravity is doing most of the work, right? So it comes down, very gentle increase. And as the signal is going down, the AV bundle, and then going towards the ventricle, there's no contraction at this time. So there's a little delay here. Okay, little delay, no contraction. It's just the signal going through the AV bundles. And when it goes to the Purkinje fibers, then that's when you have the big spike, right? We need to have a forceful squeeze from the ventricles, right? So that we can send the blood to the lungs, we can send the blood to the body, right? Hey, which side do you think produced the harder squeeze? Let me give you guys a poll here. I haven't done a poll for a long time. Just make sure that you guys are all still awake with me. Okay. So if you think the right ventricle, choose A, left ventricle, choose B. The question is, which side needs to squeeze harder? If you think it's the same hardness, so to speak, or same strength, then you can choose C. Does the right side have to squeeze harder, or does the left side have to squeeze harder? Like, what's going on here? Okay, anyone else? Gonna close the poll in a couple more seconds. Okay, so we are kind of, neck to neck between A and B. A few people say C. Well, actually, the left side, the left ventricle is going to have to produce a harder squeeze because the left ventricle needs to send the blood throughout the whole body, right? Whereas the right side, we're just sending it to the lungs. The lungs are nearby, right? The heart is in the middle, the lungs are on the side. You don't have to squeeze too hard, right? Gentle squeeze and it's going to go through the lungs and come back. Okay? So left ventricle has to squeeze harder. But that's what this big spike is. This big spike corresponds to, ventricular. Ventricular contraction. And the rest of it is just the heart resetting itself. Okay? Every time after the cell gets excited, the proper word is excited. That's what it means. When the electrical signal excites them, afterwards they have to reset before the next wave comes. Okay, so the rest of it is just like resetting. That's all. All right, more poll questions. Anyone else? Last call. Okay, you just have to look at the formula for cardiac output. It is volume of blood per minute. Okay, beats per minute is heart rate. Milliliters per beat is stroke volume. And the last one is nothing. Okay, another one here. Okay, good. This one is good. Everybody got it right. Everybody who participated got it right. It will increase because when you're exercising, your heart rate goes up, right? And the cardiac output equals to heart rate times stroke volume, right? So if heart rate goes up, cardiac output is going to go up. Here is another one to think about. If someone just had a heart attack, okay, and then they survive and then they're recovering, what do you think will happen to their cardiac output? Okay. Recovering from a heart attack. Well, heart attack is basically some of your heart muscle dying, right? Okay, and so the heart muscle becomes weaker, which means it's not squeezing as hard. Stroke volume is going to go down, which means your cardiac output is going to go down as well. Okay, so something to think about. That's all. Let's move on. Next, we will be talking about blood vessels. Blood vessels. There is this thing called the body work exhibit. It was here like 15 years ago, I think, at the Science Center. But they tour around the world. It's basically they have all these specimens like from humans who from people who donated their body for science, I guess. And you know, one of the things that they did was they had one exhibit where they dissolve everything from the cadaver, right? And only the blood vessels was left behind. And you can see all the vessels, right, covering virtually every inch of the body, right? Even if you take away everything, all the vital organs, you can still see, you know, it's going through the heart, and then you can see the aorta here, and then you can see the carotid artery going up, and it just shows that blood vessels are essential for life because they deliver nutrients, right, to all the cells in the body. So the obvious functions are listed here. Okay? They are responsible for transporting blood and its contents, and there are a lot of things in the blood that we will learn about next week. Okay? There's nutrients, but there are also waste product. There are also immune cells, and so on and so forth. And the blood vessels will allow the gas exchange to take place. Okay, so it depends on where the exchange is happening. The direction of movement is going to be different. So pulmonary capillaries, these are small, tiny vessels in the lungs. In that case, you will have, you know, O2 coming in, and we would remove carbon dioxide. But when it comes to the systemic capillaries, these are blood vessels that are throughout the body. It's the other way around, right? You will be adding, right, adds carbon dioxide, and then you will remove O2. Okay? So we talk about the pulmonary circuit and the systemic circuit, right? And we understand why it is opposite, right? Because at the tissue, that's where you need to dump off the oxygen so your cells can use it, right? Blood vessels can also help regulate blood pressure. Okay? You actually have some smooth muscle around the blood vessel. We learned last semester at the end that smooth muscles are these muscles that contracts on their own, right? We don't control it. So if your blood pressure is dropping, those muscles can squeeze your blood vessels and help your blood pressure go up. Okay? If your blood pressure is too high, then those muscles would relax the blood vessels and cause the blood pressure to come down and adjust it accordingly. Okay, I'll write this down for you at a later slide. I just want to keep this in mind for now. And also, blood vessels can help direct blood flow to body parts to meet their demands. Your body have different blood flow needs depending on what you're doing. Okay, if you are, you know, at home right now, you know, watching me talk for the past hour, then there is no need to direct blood to your legs, for example. Okay, you're not running around, so your body is gonna, you know, conserve the blood and send it to somewhere else. Okay, maybe send it to your digestive system because you had breakfast, so it's time to digest it. When you're up and running around, then you need to divert more blood to your muscles. Okay, and then you will take away blood from your digestive system. So depending on what what you're doing, the blood flow is going to be different to different parts of the body. And that is, for the most part, regulated by blood vessels as well. So I'll show you this picture. Okay? So we have an artery here and we have a vein here. And then, you know, we have a capillary network in between. So normally, this is what happens. The blood comes in, okay? And then it's gonna, let me choose a different color. This is a little bit difficult to see. Let's say the blood comes in here from the arteries, and then it's gonna go over here and fill up all these capillary vessels, okay? They fill it all in. You don't have to draw anything, you just have to watch. And then it goes to the vein, right? So that would be like full 100% supply of blood to whatever this location is. Okay, but let's say you don't really need as much blood now. Okay, let's say this is the muscle and you're not really moving around. Then there are these tiny valves or sphincters that could close off these paths. Okay? So when the blood comes, right, it's just gonna go through directly to the veins like that. It's not gonna fill up the whole capillary bed. Okay, it's still supplying blood, but because the valves are closed, you're not gonna fill up the entire capillary bed because you don't need as much blood at this moment. Okay, so the blood vessels will help you regulate how much blood goes into a particular area. Obviously, some parts of the body are too important to shut off blood flow, right? Like your brain, like you want to have constant blood flow to there. Your heart, right? All these are important places where the blood needs to be maintained, blood flow needs to be maintained, but other areas you can control. Okay, so this is an interesting picture of artery and vein. Can you give me some description as to how they are different? Like arteries and veins, side-by-side comparison. What do you notice?
The vein looks bigger and the artery has a thicker wall, it looks like.
Yeah, that's right. So for veins, they are typically larger diameter, okay? But then their wall is thinner, and I'll tell you why later. But I want you to kind of notice that for now. And for the artery, it is smaller diameter, but it is thicker wall. Okay. All right. We are going to take a note now. It's a pretty big note. You probably need to have at least half a page in your notebook. And it's an important concept that will, come back again and again throughout the course. Right, so this is called capillary exchange. Which, in a simplest sense, is basically the exchange of substances, right, and fluids between capillary and its surrounding. Okay. So there are three factors that affect capillary exchange. There are three things that will determine whether things go in to the capillaries or whether they leave the capillaries. Okay. Factor number one. That's the easiest one to understand. concentration gradient. Okay. And you know, diffusion is related to concentration gradient. So let's say we have, let's draw a capillary, okay? Now in a capillary, this is capillary, okay? Which is the tiniest blood vessels, right? Remember we learned that last time? It was one of the first thing we learned. It's like the first slide. From the heart goes to artery, arterial, capillaries, right? Before returning back to the heart, right? So capillary, that's where exchange of materials occur. It's not just gas we're talking about, right? It could be nutrients and waste product as well. So the surrounding would be like tissue. Okay. Systemic tissue, we can say, like bodily tissue, right? I mean, we can do it in the lungs as well, but you know, let's say it's systemic tissue, like the liver, maybe it's the muscle, doesn't really matter. It's just the surrounding, okay? Now, one side of the capillary is going to be connected to an arterial, right? So this is arterial side. They sound the same, I'm sorry, but I was saying it's connected to an arterial, as in like artery becomes arterial and then becomes capillary. But then we call it the arterial side as an adjective because it's connected to an artery, right? It sounds the same, I'm sorry. Doesn't really matter. Okay, one side is connected to that arteries, and then the other side is connected to a vein, right? So we call this the venual side. Okay. So which way is blood floating? Now you should know this. Is it from left to right or right to left? Which direction is the blood flowing?
From arterial to veneal.
That's right. Arterial to venual, right? Okay. Now I also want you to understand this is a simplification, right? Like in reality, you will have the artery side coming in, and then the capillary is gonna open into like a network, right? Okay, like we saw in the picture, like a network, right? Before continuing, right? It's more like a, you know, when you buy fruit, sometimes it comes with that little styrofoam net, right? That's like what a capillary is like. It's a network, it's a web. Okay, but for simplicity, because that's like very difficult to draw, I'm just gonna keep it as a tube. Okay. So, concentration gradient. This is the systemic tissue. So we're gonna have like high oxygen content blood coming in, and I'm just gonna put a bunch of O2s here. Right? This is fresh from the aorta, has a lot of oxygen in it. Okay. Systemic tissue, not so much. Okay, it might have some. Okay. Carbon dioxide very low. It's not like zero. There's still some. Systemic tissue would have a lot of carbon dioxide, right? Because of cellular respiration. So when the blood is going this way, right? It's going this way, blood flow. Naturally, the oxygen is going to diffuse out and the carbon dioxide are going to diffuse in. Do you understand that? It's pretty straightforward, right? So afterwards, you're going to have more carbon dioxide because it got picked up from the tissue. It will still have some O2, just not a lot. And then the tissue will now have more O2 than carbon dioxide. Okay, and then the blood will continue forward, right, and return to the heart. That's all. This is not restricted to gas. It's not restricted to oxygen and carbon dioxide. It can also be happening to things like, glucose. Okay, I'm just gonna use these like little green dots here to represent glucose. And the glucose is being used up in the tissue, right? So then A2 will come out. Yeah, so green dots. We'll say nutrients. Okay, and maybe we will also have the waste. Hold on. Right, we'll have some waste product here. Okay, maybe there's some waste here in the blood as well, but then they will come in. There we go. Okay. So no no energy is required. It just happens on its own. Things naturally go up and down their concentration gradient. All right. So that's the first factor. Now the next two factor is better if I can teach it continuously. So I'm going to take an early break right now, and we will come back at let's say 9:45. Okay, 9:45. Right. See you in a bit. Okay, hopefully you had a chance to, refresh yourself. We're going to continue with the note here. So we were talking about capillary exchange, which is how things move in and out of the capillaries. And one of the factors that affects this process is concentration gradient. The next factor we're going to talk about is blood pressure. Okay, blood pressure. So let's talk about the meaning of blood pressure. Like what is blood pressure, right? Blood pressure is the force of blood pushing on the blood vessel wall. Okay? The harder it pushes, the higher the blood pressure. Okay, and then that's true for any fluid, right? Fluid is liquid or gas. If you inflate a balloon, right? If you blow up a balloon, the, the the pressure that you feel when you press on the balloon is actually the force of the gas pushing at the balloon wall. Right? That's what pressure is. So in this case, instead of talking about gas, we're talking about the blood, which is a liquid. So how much force is it pushing on the vessel wall? Okay. Another thing you have to understand, which I didn't tell you yet, is that here, like a side note. I'll put a side note here. Side note. The capillary wall is leaky. Yeah. So, like if you draw the capillary again, the wall is leaky. Now, this is an exaggeration, okay? Like it's not actually like that. Okay, I mean, if that's the case, then we would bleed internally and have a horrible death. Okay? But it's leaky on a microscopic level. It's leaky. So fluid can leave and enter. Okay, I say fluid and not blood. Okay? Blood has many things in it, right? So I'm just talking about the fluid portion of the blood, which is mostly water. Okay, with some other stuff that we'll learn later. So I want you to know the capillary wall is leaky, so things can go out, things can come in. Okay, that's something to remember as we continue our discussion.
I have a quick question.
Hmm.
So is it similar to the semi-permeable membrane we learned before?
Yeah, you can think of it like that. Yeah, that's a good way. All right. Let me ask you to visualize another thing for me. Okay? Let's say we have a faucet, okay, a tap, right? Like in the backyard or something, and then you're gonna hook this up to a hose, a really long hose, okay, hose. And of course, water's gonna come out here, right? Okay, but let's just turn it off for a second, right? And then we're gonna poke holes along the hose. We're gonna put some holes here, gonna puncture it, with an ice pick or something along the way. And I want you to visualize what's gonna happen if I turn on the tap to maximum. Right? Turn it up to max. Let the water flow. What's gonna happen? Well, I hope you know that water is gonna shoot up here, right? And water is gonna come out, right, like all over the place. But what happens down here? Do you expect the water to be shooting out with the same intensity, greater intensity, or lower intensity when we're further down the hose? What do you think?
Lower.
Exactly. Very good. Right. So like it's still gonna be shooting water, probably like very similar at the beginning, right? But then the further down the hose you are, right? Lower the pressure. And if this is like a really long hose, like at the end it would just kind of be like, seeping out, right? And why is that? Why is that? Because the further away you are from the source, right? The source is the faucet in this case. The further away you are from the source, the lower the pressure is going to be, right? And that's the same thing when it comes to blood pressure. Blood pressure, BP, decreases as blood moves away from the heart. Okay, blood pressure decreases as blood moves away from the heart. Right? So I'm gonna draw the capillary again, but then the next diagram um, is gonna have several things going on. We're gonna have the blood pressure being illustrated in it, and then I'm also gonna add the third factor on the same diagram later. Okay. I mean, I don't know how your notes are, but like I would suggest opening a new paper, just to put it on the side. So I would have all the description on one piece of paper for the words, and then I would have a clean diagram to draw the things on as well. That's just my suggestions. Okay. So let's draw a new capillary, a nice big one. Okay. That. Okay, capillary tissue, right? And I told you it's leaky, so let's just pop some gaps in it. Okay, you probably can do a better job than me, but there it is. Okay, I'll give you a moment to set this up. Remember, this is the arterial side. This is the venous side. Okay, so remember the blood is going this way, right? This is blood flow. So based on what we talked about with the hose and the water pressure, water shooting everywhere, which side is gonna have higher blood pressure? The arterial side or the venous side? Let's do a poll. Here's the question. Which side has the higher blood pressure? A for arterial side, B for venous side, venous side. Which side has higher pressure? The arterial side, A, or the venous side, B? Okay, I only have 6 answers so far. I need to make sure that you guys understand before I go on further. Okay. Well, thank you for those who had participated. And you all got it right. So this has higher blood pressure. And what is the blood pressure doing? Well, just like the water is shooting out, the blood pressure is pushing fluids out of the capillaries. Okay, so we're gonna have fluid coming out of the capillary like this. Okay, remember I'm saying fluid, I'm not saying blood. It's just the liquid portion that is being pushed out. Okay, and as you move towards the venous side, it gets weaker and weaker. All right, so blood pressure here, BP, it's approximately 30 mmHg. That's the unit we use to measure blood pressure. Millimeter mercury. That's what mmHg stands for. And on the other side, it's about half of that. So 15 mmHg. The numbers are not like you don't have to memorize them, okay? Like it will make sense why I put the numbers there in a bit. Okay. The key thing here to know is that blood pressure pushes fluid, the fluid portion of the blood, okay, the liquid portion of the blood, out of the capillary. All right, I'm going to pause there for a second, just let you gather your thoughts and ask any questions you might have.
When we check the blood pressure, it mostly comes the same. So how does it is different there?
Yes, that is a good question. This is talking about the blood pressure in the capillaries. Okay, so if you measure the pressure from one end versus the other end, then we see a drop. When you talk about measuring blood pressure, we do it at the cuff, right? Okay, so that is measuring blood pressure in an artery. Okay, so in the artery, we have two pressure actually. You have two numbers, right? A higher number and a lower number, right? Okay, so that's different. We're gonna get to that in a second. But this is not in the artery in this picture, right? We talk about the capillaries, one side closer to the artery, the other side closer to the vein. That's where we see a difference in number, right?
Thank
Is
you.
that, yeah, okay. Anyone else? Are we okay? All right, now listen, guys. If this is the only force that's acting on the capillaries, then we got a problem because we are like losing fluid all over the body, right? And that's not a good thing. We're gonna swell up, right? You might have heard of edema before, right? edema, edema. That's basically what happens. In edema, you are losing so much fluid from your blood vessels and they are accumulating, they are building up in the tissue, and it causes your body parts to swell up. Okay. So we must have a counteracting force to balance out the blood pressure. Right? And that takes us to the third factor. Okay, third factor, which is what we call the osmotic pressure. Osmotic pressure. So let's explain what this is first. Osmotic pressure is caused by difference in osmolarity between between the blood and fluid in tissue. Okay. Now I'm gonna keep it very simple here. What is osmolarity? Basically, like the concentration. Okay. We did this last semester in lecture 4, I think. Okay. And people were struggling a little bit with this concept back then. But you know, if I did my job well, hopefully you will remember and understand now. Let's say we have a semi-permeable membrane here. And then I'm gonna put some solute here. That's very big. I have some solute here, okay? Now the solutes are really big. They cannot cross the barrier. You see the gaps in the barrier are like, you know, quite small, right? Okay, so my question at the time to you is, which way will water move? Okay, let's just make the thing a little bit higher.
Right to left.
From right to left, yeah. Okay, let's do a poll. Which way will water move? Is it right to left? You know what? Let's just say, is it this way or is it this way? Okay, let me do the poll with you. Okay, please try to participate in the poll. That's the only way for me to see whether you guys are with me or not. Which way will water move? Okay, yeah, much better participation this time. And you know, most of you got it right. The water is gonna move this way. Okay, remember the green dots cannot move. Okay, the green dots cannot move because the membrane is very fine, right? It's too small. The pores in the membranes are too small for the green dots to move. So the only thing that can move is the water. The water is always going to be sucked towards the more concentrated side. Remember last semester I told you if you put salt in your mouth and hold it there, the salt basically makes you drool, right? Sucks all the saliva out of your mouth. That's basically what's happening here, right? The solute is drawing the fluid towards itself, towards it. Okay, so water moves towards the more concentrated side. Okay. I need more space. Give me a second here. There we go. All right. So generally, blood is more concentrated, higher osmolarity than the tissue. Okay? That's generally true. And what's creating this concentration? Plus osmolarity is, sorry, let me write that again. Okay, so like blood cells, proteins, okay, electrolytes, all contribute to blood concentration. Okay, now please listen carefully. The blood cells and the proteins, they are really big. Okay, so they are not going to be able to sip through the gaps in the capillaries. Okay, I'll explain more when I go back to the diagram. Just write down first. Okay. All right. So let's go back to this diagram. Hopefully you have it on a separate piece of paper, and then you have the notes over here so you can see them side by side. There's no way for me to do this in a virtual setting. Usually in the classroom, I would have two whiteboards, but you know, whatever. So I'm gonna draw some dots here, okay? Like the green dots. And then not to be confused with the green dots earlier, okay? Like that's something else. This is a new diagram now, okay? You can use a different color if it's confusing you. You know what? Let's use a different color. I'm sorry. You know, purple dots, whatever, it doesn't matter. Okay, so like we have these, you know, these things. Okay. And then on the outside in the tissue, you would also have some. Okay, but not a lot. Okay, so these are various things. Okay, things that contributes to concentration, right? Okay, we'll say solute. But we know it includes things like blood cells, proteins, some electrolytes. And I know what you're thinking. Maybe you think about this, hey, won't they come out, right? Like diffusion, right? That's what we learned earlier. Some might, right? If it's electrolytes, if it's like sodium or chloride, they are very small, they can come out. That's fine. But a majority of the stuff is not going to be able to move. The proteins, they are too big to come out. The blood cells, they are too big to come out. Okay, and you will learn next class, like 45% of your blood is made up of cells, right? So that's a significant chunk that's remaining in the blood and you know, contributing to the concentration. Okay, so for that reason, these purple dots are not going to be moving in and out on their own. Okay, and more importantly, the concentration of the blood is similar on the arterial side and the venous side. Okay, like you're not going to change it substantially, all right, from one end to the other. So here's the all-important question. The osmotic pressure is created by a difference in osmolarity, a difference in concentration, right? It's more concentrated in the blood than it is in the tissue. So which way is fluid going to move? Is it going to move into the capillary or out of the capillary? You really got to think about this. Which way is, I'm going to draw some purple arrows to represent the movement of fluid caused by the osmotic pressure. Which way should they be pointing at? Into or out of the capillary?
In start, it will be out, and it will be into.
Say that one more time. We started.
In the start towards the arterial side, it will be going out, and towards the venous side, it will be inside to the capillary.
Interesting. Anyone else?
I guess into.
Into, yeah. So let's go back to this diagram, right? Look, the fluid, the water, is gonna move towards the side with more dots, right? Like all the time. Right? So if you take a look over here, there are more dots in the blood than outside, right? So actually, it is going to be moving in. Right? Remember, Mohammed, the purple dots are not going to go anywhere. Okay.
But there's
So,
more blood pressure on this side, so it will influence that too, no?
oh, I see where you're coming at. Okay, so we're just focusing on the purple dots at the moment. Okay, we're gonna forget about the blood pressure. Okay,
Oh.
just gonna focus on the purple dot for now. Okay, so we're gonna be drawing fluid in like this. Okay, like this. Okay, and because I told you the concentration is not really changing, then it's gonna be drawing in fluid with the same strength. Okay, as we go from one side to the other, it's the same arrow. Right? It's not increasing, it's not decreasing. Okay, so the key takeaway here is this. OP draws fluid into the capillary. Okay, draws fluid into the capillary. And I'm going to put some numbers here for you. Osmotic pressure, if you measure it, it's about 20 mmHg. Right, so over here is also about 20 mmHg. Okay, so write down what you need to, and again, ask questions if you have any. We're not done with the notes yet, but yeah, ask questions if you have any.
So we will not look at combinedly because the blood pressure and osmotic pressure.
We will, yeah, that's the next part. Okay, so just hold that thought, and that's where you got that idea, right? Where it's like in and out on different side, right?
Yeah.
Yeah, very good. I'm gonna get to that in a second. But I want to make sure the class, right? Like, you guys are very quiet, but like I want you to know to make sure that you understand why the red arrows are pointing out and why it is getting smaller and smaller. And you also have to understand why the purple arrows are pointing in and that they are the same length. Okay, so if you understand those two parts, then you're good. But if you're not sure, ask me something.
No, that's clear. That's good.
The rest of you okay? Remember, all these is going to be on your first quiz, huh?
Quick question.
Mm-hmm.
So the pinky kind of arrows are just random fluid that's in the blood that just wants to go out, or why does it want to leave?
The pink arrows, yeah.
Yeah.
So the pink arrow represents the blood pressure that's pushing out the fluid. I wouldn't say they're like random fluid, but they would be like the fluid portion of the blood, okay? Which is mostly water with some dissolved stuff in it, okay? And why is it coming out? Well, think of the water hose, right? Okay, when you have pressure, it pushes things out. And to counteract that force, we have the osmotic pressure. The osmotic pressure is like sucking things back into the blood vessels. So we are not like losing fluid all the time. Okay, so that takes us to the next point. If we combine these pressure, okay, we have 30 units, 30 mmHg pushing things out. We have 20 mmHg bringing it in. So think of this as like a tug of war, right? Okay, which is stronger? Well, the red arrow is longer than the purple. And if you do the math, this is a net pressure of 10 mmHg out. 10 mmHg out. So overall, you will be losing a little bit of fluid. Okay. So over here we have fluid loss. Okay. But on the other side, if you do the math over here, the purple arrow is bigger than the red arrow. So in this case, the P net is actually 5 mmHg in. And these are just like reference numbers, right? They're not like absolute. I mean, it depends on which part of the body you're in. But this is a recurring theme. You will lose fluid on the arterial side, but you will be able to gain it back in the venual side. Okay, so fluid gain from the perspective of the capillary, right? But we still have a problem here. Does anybody notice a problem here? Like, what is there something that doesn't quite make sense in this
Yeah, because
procedure?
net pressure on entrance is more than the exit, so there will be more fluid loss than the fluid gain.
That's excellent, right? Exactly. Look, on the arterial side, the pressure is 10. There's 10 unit of pressure pushing things out. But on the venual side, we only have 5 unit of pressure bringing it back in. What that means is, even though you're bringing in some of the fluid, you are not able to bring back everything. Okay? So some of the fluid that is lost will stay in the tissue. All right? And it turns out those fluid that stays in the tissue plays an important role as part of your immune system. And we'll come back to this concept later at the end of lecture 2. Okay, for now, we're just gonna leave it as it is. Okay, for now, you just have to contend with the fact that, okay, I'm losing more than I'm bringing out. Okay, but what's happening to those extra fluid, we'll find out later next week.
Will it not cause swelling or problem?
As you will see next class, it will not. Okay, unless the balance is really drastic, right? You will see there is another drainage in the body that will help return those fluid back into circulation. Okay, but that's the next class. All right, that was a very, very long note. You know, maybe you want to watch that again in the recordings. But let's just go back to the PowerPoint for now. I have a few poll questions here.
Can I see the bottom part of the note one more time, please?
Sure, like here.
Yeah. Thank you.
Yep. Let me know when you're ready, and then we'll go. Yeah, but this concept is particularly important, okay? Like we're going to come back to it several times in the course. When we talk about the kidneys, we will refer to this concept again. When we talk about the brain, we'll talk about this concept again. It's like a reoccurring thing. That's why we spend so much time
Thank you.
talking about it. Yeah. Okay. So here we go. I will let you read it first, and then I'll launch the poll. Okay, that was a minute. Most people got it right. If you look at the picture we just drew, the arterial side, which is right here on the left, the BP is greater than the OP, and then it's pushing it out. Okay, so the correct answer is A. A. So I mean, like this is definitely a diagram I will have next to me when I'm doing the quiz as reference, right? I mean, even better if you can memorize it, but it doesn't hurt to have it there by your side. Okay, what about this? Which of the following is true about osmotic pressure? Okay. Venus is same as Venus side, okay?
These are the same kind of questions we will see in the quiz.
Some of them, yeah, some of them. Not all of it, really.
It will be only per multiple choice or some writings as well.
No writing, no writing. Everything is multiple choice. Yeah, some questions might have more than one correct answers though. Okay, so. And it will tell you in the question. The question will say select all correct answers, right? Then you will know those are the ones that have multiple answers. Okay, this one is causing a bit of a problem, it seems. Anyone else? Last call. All right. So let's see. We're talking about the osmotic pressure. Let's look at our picture here. I hope you've drawn this in color, okay? Like if you draw in black and white, it just doesn't really have the same, you know, it just doesn't give you the same kind of information, right? So which color is osmotic pressure? Is it the red or the purple, huh? Purple, right?
Purple.
Yeah, thank you. Sorry. Purple, yes. And look at the purple arrow. Is it changing from one side to the other? No, it's 20 on the left side and 20 on the right side, which is why the correct answer is C. Right? It's C. Right? Why is it the same? Because the OP, the osmotic pressure, is dependent on the concentration of the blood and of the outside, right? And these things don't change from one side to the other. And that's why OP is the same. BP, on the other hand, will drop, right? So that's that. All right. So that's the end of another big concept. See, now you understand, right? Why the quiz only has one lecture on it and then the test will only have 3 lectures because it's a lot of material that you have to go through and study for the quiz and test. All right, so don't wait until the actual test. Don't wait until the actual quiz. Start studying, today, preferably. We still have quite a bit to go to finish the lecture, like 20 more slides to go. So, buckle in and hang in there. Next concept we're gonna talk about is venous return. Okay, venous return. Venous return is basically sending blood back to the heart. Okay, sending blood back to the heart. There are 2 main challenges with this. Right? Challenge number 1, if you think about it, this is the person, and the heart is right here. Right? So the blood has to go against gravity. Right? All this blood at the bottom of the body has to go against gravity to return to the heart. Right? So that's a challenge. And challenge number 2 is low pressure. Remember, by the time the blood passes through the capillaries, the pressure has dropped quite a bit. Right? It's half of what it used to be. And whenever we are in a low pressure system, fluid don't travel very fast. Now, if you live in a house, you might have this experience before. Okay, let's say there are like this is the main floor, and then this is the top floor. Okay, when you try to take a shower at the top floor or something, and then you are doing the laundry at the same time, okay, then the pressure from the faucet might drop, right? Because you are diverting a lot of the fluid to other appliances that uses water, right? So the low pressure causes the fluid to have trouble going up, basically. So those are the problems, those are the challenges that needs to be overcome when we try to bring blood back to the heart. So how do we fix those problems? Well, we use what's called a skeletal pump. Skeletal pump. Okay. So basically, in this diagram, you can see these are muscles in the legs. Okay, in the calf. Okay. So anytime we walk, anytime we move our legs, the muscle in the legs is going to contract, and that contraction creates a bit of a pumping action in the veins. So that helps squeeze the blood upwards. Okay, but it's not a really strong squeeze. It squeezes a little bit, the blood goes up a little bit, and it's just going to fall back down. But we have valves in the veins. Okay, so after the muscle squeeze a little bit, the blood goes up, and then it drops down, then the valve will catch it. And the next time you will contract your muscle again, it will go up a little bit further and a little bit up further, and eventually it's going to make it back to the heart. Okay? That's why I don't know if you had this experience before, but if you are on a particular long flight and you just sit there the whole flight without getting up, and you take off your shoes and make yourself comfortable. At the end of the flight, you might find that you have trouble putting on your shoes. Your feet has swollen a little bit, right? Okay, that's because if you're not walking around, then the muscle is not really contracting, and the blood starts to pool at the lower legs, okay, in the foot. Okay, when there is more blood pooling in the leg. All right, let me go back to this diagram. Everything is related. When there's more blood pooling in the leg, the capillaries in the leg will have higher blood pressure. And that will cause more fluid to leak out, right? And as a result, your leg swells up a little bit. Okay? So that's
Question?
it. Yeah.
can that also cause like a clot or something? I think I heard something about that.
Yep, you telepathic. Well, that's like my next slide right here. Okay, so varicose vein, some of you might have heard of it. It's quite common. Okay, yeah, and it could start off as spider veins. Some people call that. It's like your veins are very prominent in the legs, and that is when the valves are not really functioning properly. Okay, so when the valves and the veins are not, it's like not closing properly, then the blood will shoot up, but then when it falls down, there's nothing to catch it. So it's like going up and down and up and down. It's never really gonna make it back to the heart, and it starts to pool in the veins. Okay, and then it starts to have these prominent bulges, right? Okay, and it could hurt sometimes. It's uncomfortable, and it also increases the risk of getting a blood clot, right? We call that thrombosis, right? Some of you might heard of deep vein thrombosis, right? So that's like a blood clot that's forming in the veins, okay? This could be sometimes a permanent situation. So does anybody know what people need to wear for this situation? Like you might know someone who has varicose veins, or like you might have it. Like what do the people often prescribe?
Compression stocking, so like tight socks to help everything keep moving.
Exactly, right? So like you wear these compression stocking that basically it's elastic, it's stretchy, and that elasticity is gonna help empty the blood, right? Okay. My wife, when she was pregnant the second time, like my second daughter was a really big baby. Like, it came out was like huge, okay? But that also means it was a challenging pregnancy because of all the weight that's in the uterus. Right? All the extra weight is putting pressure on the legs. And even though like when you're walking, all this blood is trying to go up, but that extra pressure from the baby is pressing down, right? So my wife actually couldn't fit in any of her shoes anymore in the third trimester, and she's getting all these like bulgy veins in the legs. So sometimes pregnancy, can cause this to be like a temporary, right, situation. People who stand a lot in their jobs also could develop these kind of problems. So that's why, like, if you ever had me for like in person learning, you see me like walking around the classroom all the time, right? Even when I'm just talking, I'm pacing back and forth, right? Because I try to get my circulation going, right? And even I'm trying when I do online, sometimes you see me standing as well, right? So that's part of the reasons. But yeah, that's varicose veins. Okay.
I have a quick question.
Sure. Yeah.
So in this person's legs, the veins, they don't look like they're going up and down. They're kind of going sideways. Is that because of the varicose veins, or is that how veins are? Because that
Oh,
feels
yeah,
like
that's how veins are. Veins is not straight up, straight down. It's like a network, right? So it's sideways, upwards, and all over the place. Yeah.
kind of weird. 'Cause it feels like going up and down would make their job so much easier. Like
No, but
highways.
I understand your point, right? But then there is no one single straight up thing, right? Because then remember,
Mhm.
your whole leg is gonna have blood vessels, right? So it's more like a web that comes together. But when it gets closer to the heart, then they all merge together to form that single inferior vena cava, right? So that's where they all converges and form the highway, like you said, right? Does that make sense?
Okay, yes, thank you.
Mhm. All right. Moving on. Blood pressure. We have talked about blood pressure quite a bit up to this point now, but what we're gonna focus on is how the blood pressure changes as it goes through your circulation, as well as some of the factors that would affect the blood pressure. Okay, most of the things in this slide we talked about already, right? It's just a definition of blood pressure and how it changes as it goes through the circuit. Like it declines, right, as you go further and further away from the heart. And we measure blood pressure using two numbers, okay? The systolic pressure and the diastolic pressure. Okay? More on that later. But systolic is the adjective of systole, right? Earlier today, we learned about systole. Systole means contraction. So that's the pressure that is measured when your heart is contracting. specifically when your ventricles are contracting. So that's the higher number. And the diastolic pressure is measured when your heart is relaxing, right? So that tends to be a lower number, okay? So anybody remember the textbook numbers? Like even if you take your blood pressure at like the pharmacy or something, you stick your hand in that machine in Walmart or at Shoppers Drug Mart, right? You know, they tell you like the standard numbers, right? Anybody remember what those are?
120, 80.
Yeah,
120
120
over 50 or so.
over 80. Yeah, 80 is
All right.
probably yeah. So the 180 over 80 is like the you know, the standard, okay? But it's actually not universal, okay? It really depends on a lot of things. It depends on the person's build. It depends on the person, you know, medical history, okay? So some people, if you are in your 20s, right? Like 120, 80 is actually not that great for you, okay? Like yours should be a little bit lower, right? Like maybe 110 to like, you know, 75 and so on and so forth. You know, so like when you do nursing stuff, right, they will probably tell you more about it. Okay, so what are some factors that could affect blood pressure? Okay, so total blood volume, that's a thing. Okay, the more blood you have, if you increase blood volume, you would increase blood pressure. Okay, how much blood does an average person have? How many liters? Any guess? Anybody? How many liters ballpark? You know, 1 to 5, 5 to 10. Give me some numbers.
4.2.
That's a very precise number. Very good. Yeah, roughly 5 to 6, okay? Depending on your build, depending on your gender and all that kind of stuff, okay? So all these volume is going to contribute to the blood pressure, okay? So people who suffer from high blood pressure, people who suffer from chronic high blood pressure, sometimes they take a pill called diuretic. Okay, diuretic, also known as the water pill. Does anybody know what that is? Anybody know relatives that are taking things like that, or you know, maybe you are taking it? Do you know what the water pill does to the body? No, eh? Okay, so that's fine. Diuretic or the water pills, when you take it, it makes you pee. Okay, it makes you pee more. So why is that a good thing when you have high blood pressure? Well, I just told you, high blood volume is going to contribute to high blood pressure. So if you suffer from high blood pressure, you want to pee more. You want to pee the water out of your blood, right? So that lowers your blood volume, controls your blood pressure. Okay. Stroke volume. Higher stroke volume equals to higher blood pressure, which makes sense. Stroke volume is how much blood your heart is squeezing out every time it beats. The more blood it squeezes out, the higher the blood pressure. Right? Next one, vessel diameter. Earlier, a few slides earlier, I was telling you that the vessels can expand or contract to help regulate your blood pressure. So there are two things here. It could be vasoconstriction. Okay, vasoconstriction means smaller blood vessel. That will increase the blood pressure. Think about squeezing a balloon. When you squeeze a balloon, the pressure goes up. The opposite is vasodilation, which means is bigger. The blood vessel is bigger, and that will drop the blood pressure. Okay, so these are some things that will change your blood pressure. And of course, you can do other things that would affect your blood pressure, right? You can what kind of foods should you avoid when you have high blood pressure? Anybody knows that?
Salt.
Yeah, salty food, right? Exactly, right? So, you know, by taking salty food, I will explain to you later again that it will increase your blood volume. It will increase your water retention, and then it will increase your blood pressure. Okay, so like, there are many other factors, but these are some of the examples.
Professor, is that the stroke volume should be the same?
The stroke volume should be the same. No, so stroke volume, like higher stroke volume means you're squeezing out more blood per squeeze, right? So you have all these fluid all these blood that's passing through your blood vessel. If there's more of it going out, then the blood pressure could spike, right? Imagine sorry, go ahead.
The squeeze depends on something, or like, is it not standard with everybody, or is it?
Oh, no, it's not. The strength of the squeeze depends on the heart muscle, right? So your heart might squeeze harder when you're exercising. Okay, people who constantly work out a lot, then their heart muscle actually gets stronger, and then they have a higher stroke volume. Okay, so people who have high blood pressure, they are not advised to lift weights, because it adds extra strain to your blood vessels, right? Okay, so normal blood pressure we talk about is 120/80 mmHg, but normal in quotation. All right, so I'm going to show you 3 graphs, and they are all quite important. Okay, let's take a look at this first graph here. This graph shows you how blood pressure changes as it moves away from the heart. So obviously aorta is closest to the heart, so the pressure is really, really high. But what's interesting is that the pressure actually is fluctuating at the beginning. Okay, so if you measure the blood pressure in the aorta, it can be anywhere between 120 to 80, which is the number that we were talking about, right? The healthy number, right? Okay, that's because it depends if the heart is contracting or relaxing. If it's contracting, it could go as high as 120. If it's relaxing, it could go as low as 180. Okay, but what's interesting is you can see the fluctuation eventually disappears. When you get to the capillaries, it's just one single pressure. Okay, that means when the blood is in the capillaries and beyond, you are so far away from the heart that you no longer feel the effect of the contraction and the relaxation. Once you are at the capillary and beyond, it doesn't matter whether the heart is contracting or relaxing, you will still feel the same pressure because you are so far away from it. Okay? It's only at the beginning that the pressure will fluctuate when the heart is squeezing or relaxing. Okay, but once you're too far away, it doesn't really matter. Okay, so you can see at the beginning of the capillaries, like the arterial side, that's around 30. After passing through the capillary, right, it drops down to about 15, which is what we had in the notes, right? Okay, the further away you are, the lower the pressure. And when we are measuring the blood pressure, we put the cuffs here, right? That's like taking the pressure in the brachial artery, right? So that's a pretty large artery, which is why the number is very, very close to the true value. Okay, it's like straight from the heart. Okay? So the higher number is when the heart is contracting, and then the lower number is when it's relaxing. Okay, so that is the change in blood pressure when the blood moves away. You have some fluctuation in the beginning, but overall it's going down. And then you have like almost no pressure when it's in the vena cava. Okay, so that's the first graph. The second graph, this is 2 graphs in one. Okay, so I want you to focus on the velocity one here. Okay, velocity means speed. So how fast is the blood, flowing in the blood vessels? Okay, it depends on 2 things. Depends on 1, blood pressure. higher BP equals faster. And again, that makes sense. Okay, that makes sense. Right? If it's really high pressure, things tend to shoot out faster, right? Again, think of the water tap, right? Or like a water gun. Right? If you have kids, you might have seen water gun, you know, the one that you pump up the pressure and then you shoot it out very fast at the beginning, but as you lose pressure, it just like, you know, start to decline, right? The stream. And the second factor, the speed, okay? The speed of blood flow, the second factor that depends on is the vessel diameter. People tend to get confused with this concept about the diameter. Okay, just think of the diameter alone. Okay. Do you think it's faster in a bigger vessel, or do you think it's faster in a smaller vessel? A for bigger, faster in bigger. B for faster in smaller. Which one is faster? Bigger is faster or smaller is faster? Just the vessel diameter, okay? Don't think about the pressure. Just think about the diameter. Okay, yeah. Anyone else, by the way? I got my usual 12 responses. Is the other 4 people like not here, or like are you not seeing the poll? You can just message me and let me know, okay? I'm just curious. Okay, see, this is what I mean, okay? People think the smaller one is faster, and I kind of understand why, okay? I'll get to that in a second, okay? But like think about another situation. Think about driving on the street. Are the traffic going to be faster when there are more lanes or less lane? Like if it's like a 4-lane, 5-lane highway, is that faster or compared to like a 2-lane street? Which one has faster traffic? Well, common sense hopefully tells you. Yeah, go ahead, Tohib.
I think it's the one that has different lanes. Like people have different options to pass.
That's right. The bigger the road, the wider the road, the faster, right? So when it comes to vessel diameter, like if it's bigger, it equals to faster. Okay? I sort of understand why people choose the smaller one. Because you guys are also thinking about blood pressure at the same time, I'm guessing. Right? You're like, oh, if it's smaller, then the blood pressure is higher, then it's gonna be faster, right? Okay. But we are looking at this like separately. Okay, we're looking at blood pressure as one thing on its own, and then we're looking at diameter as one thing on its own. So if all else remains the same, if we just look at the diameter, then bigger is faster. Okay. Once we start to put like try to put everything together and think about how this affects that, then you know we can very easily get tangled in too many things, and you know we can come up with a direct correlation anymore. Okay, so that's that. So let's take a look at here. This is the graph that we are looking at. Okay, so the velocity is going to be going up and down a little bit at the beginning, which makes sense because look, velocity depends on blood pressure. And we know from the previous graph, blood pressure goes up and down at the beginning. So if blood pressure goes up and down, then velocity is going to go up and down as well. Okay. And then it's going to drop substantially at the capillaries. Okay. So it is the slowest at the capillaries, which also should make sense to you because at the capillaries, that is where you are exchanging nutrients with the surrounding, right? You are doing gas exchange. If the blood is going by super fast, you're not going to have enough time to do that. You're not going to have enough time for diffusion. So you need to slow down substantially so that you give them enough time for the diffusion to happen. Once you get past the capillaries, then it speeds up again. Remember that picture that we had before? You don't have to go back. I'm just showing you. Like, look at this picture. Look at how big the vein is. Right? Vein is large in diameter. So because it's really big, right, it's able to speed up again. Okay. So at the beginning, at the arteries, even though arteries are smaller, but it's high pressure, that's why it's still fast. On the vein side, even though the pressure is low, but because it's really big, it's able to pick up the speed as well. So that's how the velocity change. Finally, we have what's called total cross-sectional area. And that means if you lay out all the vessels on the floor, which one covers the most area? Okay. So aorta and arteries, they don't cover as much area. Even though aorta is really big, if you remember that picture I showed you, right? The one I took with of the real heart, I told you if you stick your thumb in, there's still a lot of wiggle room. It's really big, but you only have one aorta, right? So collectively, it doesn't cover too much area. Capillaries, on the other hand, it's really small. You can't even see capillaries with your naked eye, but it's covering your entire body. There's so much of it, right? So collectively, right, it has the highest cross-sectional area, right? It's able to cover the most area. All right, so those are the three things that you have to know. Okay, high blood pressure, hypertension, right? So that's the inability to regulate blood pressure, and you are going to get hypertension. So that is when you have a resting blood pressure higher than 140 to 90. Okay, resting is like you sit still for like some time, right? Okay, or like if you naturally wake up in the morning, not to the sound of your alarm clock, not because your kids woke you up, like you just woke up naturally, you have a good rest. That's your resting blood pressure. Okay, and even at that point, if it's higher than 140 and 90, that's hypertension. Okay, so it's not good. High blood pressure is it's not good for the heart. It's not good for the kidneys, as you will see. It increases the risk of getting heart attack, heart diseases, as well as kidney failure. It could be hereditary, right? Diet can contribute to it. Okay, if you eat a lot of fast food, right, the sodium, the grease, all that things can contribute to high blood pressure. Okay, so remember this picture, right? The capillary. If you eat a lot of sodium, right, in your diet, I'm not talking about like 1 or 2 times. Okay, if you have, KFC for lunch today, that's okay. Your blood pressure is not going to change too much. But if you constantly intake a lot of salt, then the salt is going to be in the blood, right? Look, you're going to increase the osmotic pressure in the blood. So now you will be, those purple arrows that we drew, now they will be longer. You'll be retaining more fluid. So that increases blood volume, which then increase blood pressure, right? And so diet can affect your blood pressure. Okay, poll time. Right, this one is kind of all over the place from the way that people are answering. Okay, let's just go back a few slides here. Look at the blood pressure graph. Okay, as you move away from the heart, the blood pressure gets lower and lower and lower and lower, right? So it's the lowest. It's the lowest at the veins. Okay, at the veins. I know what some people are thinking. Okay, they're thinking, okay, heart, artery, arterial, capillaries, veins, venules, and then veins. They're like, hey, the veins is really close to the heart. Okay, so shouldn't it be high? No, we're talking about like from start to finish. There's directionality associated with it. Okay, it's a one-way street, right? Okay, so the blood pressure as you go this way around drops until you get to the vena cava, the veins, lowest. Let's try another one here. Okay, anyone else? Okay, so blood flow velocity is speed is the lowest. That means it's the slowest, right? At capillaries. Remember I said, remember the graph. Graph goes like this, okay, for velocity. Okay, it's the slowest at the capillaries because we have to slow down substantially. We have to slow down enough for gas exchange to occur. If blood is zooming by very quickly in the capillaries, you won't have enough time for diffusion. So we need to slow down. Slowest at the capillaries. Okay, so blood pressure is the lowest at the veins, but speed is the lowest at the capillaries. All right, this one is a little bit challenging. Okay, correct answer is C, high pressure and large diameter. If we go back to the slide here, it says velocity depends on BP. Higher BP is faster, bigger is faster. So if I can have something that's really big and really high pressure, then it's gonna be the fastest, right? Okay, so really big and really high pressure. Okay, this is gonna be the last slide for today, and then we will finish up the lecture next time. But we have a bunch of things here. I'll give you a minute or two to fill this in. Okay, so which one has higher pressure? Is it artery or veins? Right? Okay, just go through the list. I'll give you a minute or so, and then I'll take it up with you. Just ignore the word lumen. Okay, lumen just means the inside. Okay, inside of the vessel. Okay. First one, higher blood pressure. After everything we talked about, I hope you know is artery. Thicker vessel wall. Thicker vessel wall is artery. Okay, remember that picture, the one with the blue and the red, right? And now you understand why the artery needs thicker walls. The thicker wall is able to help withstand the pressure, right? If the wall is thin and the pressure is really high, it can rupture and cause all sorts of problems. Larger diameter, right? Lumen is referred, like if you have a hollow structure, the inside here, that's called the lumen. Okay, like the lumen of the stomach, that's where the food goes. So the lumen of the blood vessels is the inside. Which one is bigger? Again, think of that picture, right? With the blue and the red, right? Remember that picture, right? A couple slides ago. So it's larger for veins. Valves is found in veins. Remember the venous return that we talked about? The blood goes up and drops. You got to catch them. Blood has a higher velocity in arteries. Carries blood away from the heart. Okay, that would be, artery. Okay. We still have a few more slides, but I think it's 11 already, and I know we already learned like a lot. So we'll do it next class. We will also start on lecture 2 next week. Okay, so please start studying. Please email me if you have any questions, or if you have suggestions about the course. You can of course email me as well. That's it for today. Thank you for coming. Have a good rest of your week. Take care, guys.